Okay, so this is the 3.2 Foundation All Questions booklet for Year 10, and the code is there. These are the equations that you'll find in the front of the book, and some multipliers just down the bottom there, but I don't think we'll be using as much today. So let's get through this. We'll try and do it in two parts. So we've got a little bit of information there about a homeowner who has bought some solar panels, and it's got some information here regarding how much return you get, how much the export tariff is, but we'll be looking at this a little bit later. So that's all I've done is highlighted some key information just in case I'm going to need it. The first question is a fairly simple numeracy question, complete the table. So you're just looking for a pattern here to fill this in, complete the table there. They go up 840 each time, so you just got to recognize that pattern. Very common in a paper like this, so just look out for that pattern there. Calculate the annual energy output for each meter squared. So your annual energy is in this column. Okay, and if we can look here, the roof area there per meter squared, so I've got 7 meters squared, then it goes up to 14 meters squared, then 21, 28, and so on. But it's looking here for each meter squared, so I'm going to have to divide by 7. How many times does 7 go into this figure, this annual energy output here, which is 840? So if 7 is worth 840, what's 1 worth? Well, it's going to be 7 into 140. It's going to be 120 kilowatt hours. That's the first page. So the second page, we're going to be using information from that other page there. It says they install 28 meters square of panels. During the first year, they use 3,000 kilowatt hours themselves and export the remainder to the national grid. So they're generating, let's have a look how much they're generating, and let's have a look at how much they use. Well, they're using 3,000. They're generating, and how many is it? 28 meters squared. So we're looking at this one here, 28 meters squared. How much are they generating? The energy output, 3,360. So we go back to this now. So that's why I've said, well, they're generating this much. They're using this much themselves. How much is spare? It's 360 kilowatt hours. Calculate the income that household receives from this export tariff. So I'm taking these now, this energy that they've not used. I'm timesing it by 5 because it says there the export tariff. Well, if we look in that little bit of blurb here, the export tariff is 5 pence. Again, it's a really common technique used in an exam like this where you're looking for information from the question. Okay, again, it's a really simple numeracy question because you're just timesing it. So if it's 5 pence per unit, then there's 360 units there. So it's going to be 1,800 pence, which is also £18. And they'll accept any answer there, okay, because there's no unit. Calculate the money saved by the householder by generating this amount of energy. So they've used 3,000 there, okay, so that's the figure I'm going to be using because they're saving. If we look back to the first page again, it says there the householder also saves 16 pence from every kilowatt hour they produce. So they produce 3,000 that they use, okay, and we're going to times that by 16 pence. That's what they save. They save 16 pence for every unit. When I times that together, it comes out to 48,000 pence, which is £480. So they save quite a bit there. Give 2 reasons why the annual energy output from the solar panels can only be estimated. Well, it's worth 2 marks, so you need 2 good reasons. The hours of sunshine each year will vary, okay, so you can't really predict how much sunshine we're going to get. And also the angle of the roof will vary on each house. So this is why you can't really be that precise on how much each household will save on solar, because every house is at a different position and a different angle, okay? So that's your 2 marks there. On to the next question then. I think we've already established here that this paper, this unit, comes with a lot of information. Okay, so this is the second question we've looked at. Lots of information here. I haven't underlined anything yet because there's no numbers. And then we've got a table here saying, telling us some maximum power output, the lifetime, Commissioning cost. This word commissioning is how much it costs to build. And then you'll also you get familiar with a word called decommissioning, which is the cost of taking like a building down or dismantling something. Okay. Then we've got the waste. So you can see that the wind produces no waste there, but the nuclear power station does produce radioactive waste and so on and so on. We'll have a look at this table in more depth. And then we come to a 6 marker. Use the information in the table and your knowledge. So this is going to be a mixture of both to decide which method of generating electricity they should recommend. Okay. So if this was a 6 marker, I would be expecting you to get 3, maybe 4 marks just from the information in the table. Okay, and we're going to look at that now. So I've said about a wind turbine, and then I've split this up. You wouldn't want to do this in an exam. You would want to paragraph this. You would want to maybe make these notes yourself on a bit of paper, on a scrap bit of paper they give you, or you can use the back of the book or whatever. And then I would be putting this into sort of sentences. This linked all up in a paragraph. But I'm just going to do it here just to highlight what's different and why it's beneficial. So the wind turbine, we can see that doesn't produce any harmful waste. Okay, it does not need a supply of fuel. Where's the... Is that there? Let's have a look. No, it doesn't. So that's come from our knowledge. Output is lower and will vary with the amount of wind. So the output there... Where's the output? Yeah, it's 3.6, and it's got a massive output on the nuclear power station, so that's going to be a benefit there. Lower lifetime, so it will need replacing more often. Let's have a look at that. So the lifetime there, 15 compared to 50 there. Okay, and that's in years. And then the last one I've put is similar carbon footprint. Let's have a look if I'm right there. So where's your carbon footprint? 5 to 4.8 there. So yeah, I mean reasonably similar carbon footprint, the amount of CO2 that they release per gram there. And then for the nuclear power stations, I've said that it does produce radioactive wastes, which needs to be buried. So that's it's going to cost money. Needs a supply of fuel, so we need to supply it with fuel. So that's again come from our knowledge. It's very expensive to build. Commissioning cost there, 4,000 or 4,000 million, whereas this is just 4,000. And then it's got a very high lifetime, so it's gonna last for 50 years at least there, and it's got a high output of energy. So, you know, you should be getting at least 3, maybe 4 marks from a question like this because the information is given to you. Question 4 then, another wordy question. Look, it's got all this information, but a really simple 2 marks in my opinion. Okay, you're just matching them up. So your nuclear power station, high decommissioning cost. We just talked about that. That decommissioning is going to cost a lot of money to take that structure down. The wind farm is very unreliable because you can't really rely on wind. You can't predict the wind, and if it's not windy that day, you're not going to get any energy. And then your coal-fired power station is the only one that's going to release CO2 emissions from these two, okay? Just a quick note, nuclear power station, often the misconception is that it's a renewable energy. It's not a renewable energy because it will eventually run out one day because it does need that fuel source. It needs that nuclear power, that nuclear element. Then we've got the energy input to a nuclear power station here is 20 megajoules. Now, a megajoule is just, if we look back to our first page, so it's worth doing this, we can see that it's times 10 to the power 6. That just means 6 zeros after it. So we're looking at a million after that number. So if we go back now to megajoules, so that's 20 million, isn't it? At 40%. Let me just zoom out a little bit. And there we go. And then we've got another one, which is coal-fired power station, is 20 millijoules, and its useful energy is 8 megajoules. Okay, so the question is going to be compare these two. And because this student suggests that the power station, the nuclear one, is more efficient, do you agree with this? So we're going to have to use that efficiency equation now. Now, I don't think this is given to you in your exam. Let me just check this. Efficiency. Yes, it is. It's given to you there. So you're looking for percentage efficiency. You're looking for the energy that's useful over the total energy supplied, and then you're going to times that by 100 because it's a percentage. So we're going to drag that equation over. Where are we? I'm down by here, am I? No. I've lost where I am. Right, I'm on this page, of course. So I've dragged that equation over, useful over total times 100. Well, let's have a look at the coal-fired power station. Its total, okay, is 20. And its useful output energy is 8. So I'm going to put 8 because it's useful over 20 over total times 100 because it's a percentage, and it comes out to be 40%. Why do I disagree? Because this student is suggesting that nuclear is more efficient. Well, they're both the same, so it's not one is more efficient than the other. And there's your 2 marks for that. Okay, so we're going to go down. I think we're going to leave that video there. So this is going to be the start of video 2. Okay then, this is the start of video 2. State one advantage of the national grid. So the national grid is reliable because it responds to a change in demand 24 hours a day. All these power stations are connected up, so they can all be connected as backups. That means if one power station goes down, then we can pull electricity or power or energy from another station. Okay, and they respond to a change in demand. So if everyone's got their TV on at 6 o'clock in the evening, watching Emmerdale Farm or whatever, the electricity demand is going to be very, very high. Therefore, we're going to need a lot of energy from these companies. So they're going to respond to that. Which of the transformers A, B, C to F is the step up, which is going to take the voltage up? It's going to be A. It's going to take that voltage to 400 kilovolts there. And if we look back at our prefixes, the kilo is just 1,000 of that. So add another 3 zeros onto that 400 and you get 400,000 volts there. As we can see now, they got step down transformers because that goes to 132 kilovolts and so on until you get to 230 volts, which we use in a standard home or in your school. Explain why step up transformers are used in the national grid. If we increase the voltage, we're going to reduce the current. Now this is a power equation, okay? So as you can see, I've done it by here. That if we say that the power is a constant 10, okay, I've just picked any value there, 10 equals either 1 times 10, so if the current was 1, voltage is going to be 10, but 10 can also equal 2 times 5, can it? 2 times 5 is 10. Well, I'm increasing the current now, but the voltage is coming down. And I'm going to keep it at 10, so if I put the current at 10, then that voltage has got to be 1. So that's the link there. Not that you have to prove that for 2 marks. I just wanted to show you that if you increase voltage, you're going to reduce current. Now, this is important when a power, not when you've got VIR, because now they're going to have a direct relationship. As you take voltage up, your current's going to go up for the resistance equation. Just worth noting there that these two are different, okay? Even because that's dealing with power, this one's dealing with resistance. The power one is the power station, obviously. So that's why as current goes up or voltage goes up, current gets reduced. And the reason we want to reduce current is to prevent the heat loss. Too much current is going to give us a lot of resistance there. Therefore, we need to reduce that by upping the voltage. Next page then. This is a heat transfer question. It's got a little bit of a diagram there showing what's happening. You've got some soup, which is obviously a liquid. So the heat is transferred through the base of the metal pan by conduction because metal is a solid, so it's going to be through conduction, touching particles vibrating from hot to cold, okay? All of the soup becomes heated by convection because soup is a liquid, so we've got convection currents. And then the handle is made of plastic because plastic is a poor conductor, or you could, the other option could be it's a good insulator. Okay, it doesn't transfer heat, it doesn't transfer electricity. And it's black because black is the best color at emitting infrared by radiation. And that's what we're looking for there. Sankey diagrams. Remember now, very closely linked with our efficiency equation at the front. If 400 is going in, kilojoules, and kilo is just 1,000, whatever the joules is, so that's going to be 400,000 joules going in. You've got 300 coming out as useful because it's in this direction, and I've got light energy being wasted here. Well, 400 minus 300 is going to leave us 100. So for 1 mark there, it should be a very simple answer. And again, for 2 marks, they're giving you the equation here. Don't forget it's at the front of your book as well. They just want you now to calculate efficiency. Well, it's useful over total. My total was 400 going in. My useful was 300 going across. Times 100. That 100 is not wasted. That 100 is coming from this percentage efficiency there. Okay, so don't think that is the 100 from there. It's not. Okay, it would be 100 no matter what that number was, because it's a percentage question. It comes out to be 75% efficient, which is really, really good. Okay, so where is that going to lie within this scale where we've got these categories here? So if it's 92 to 100% efficient, it's going to be in a category A or band A. So this one, you can see 69 to 80, 75 ranges between those. So that's where it's going to be. So the answer is C. Lovely. Discuss the importance of buying an appliance which has a high energy efficient rating, for example, a band A. Now, this question is going to come up somehow, and this is the 3-mark standard answer. Oop, I didn't mean to do that there. I'm still recording, yep. So what you're going to say is less energy means that less fuel is being used, okay? So less energy, less fuel. If there's less fuel being used, there's less CO2 being produced, right? Because there's less fuel being burnt, therefore less CO2. If there's less CO2, then there's less greenhouse effect. There's less contribution towards greenhouse gases and global warming. That is your 3-mark answer. Less energy means less fuel means less CO2 means it's not impacting our environment so much. That is probably, it's really probable that that sort of question is going to come up, because every exam board loves asking about contribution towards greenhouse gases and global warming. It's just a standard question. So we may as well know it for 3 marks. This is a simple 3 marks. Less energy, less fuel, less CO2, less greenhouse gases. Chemistry as well, this comes up in a lot. Okay, so another wordy question. We know that the second topic in Year 10 is going to be all about reading. Okay, so again, I'm not going to read through this because I want to kind of keep it to 2 videos. But we've got this graph here showing a number. So it's a bar chart showing a number of types of energy, or where we get our energy from, the sources of energy, I should say. I've highlighted there maybe a couple of things I need to know. So a gigawatt hour, now we're looking at that G. If we go back to our prefixes, I think that's 9 zeros after, but it doesn't matter because we're all in the same sort of, we're all reading from the same sort of gigawatt there. So we don't have to worry too much about that. Let's have a look, read of the question, see if I need to go back. In the article published by these, the energy, blah, 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 discuss what this term means for the future of electricity generation in Wales. A low-carbon revolution. Does it say in the... I can't remember now. Let me just press pause. Okay, so I just had a quick read through that. And yes, it does kind of say about greenhouse gas emissions, about this low-carbon revolution. So if I just drop down now, that's what I've said is less fossil fuels used to generate electricity means kind of what we just discussed, less CO2 being produced. It's only worth 2 marks, so I've not gone on to say less impact on environment there. But again, those are very common 2 bullet points there. Less energy means less CO2. Less CO2 means less pollution, really. Use figure 1 to identify the trends in the generation of electricity using different energy sources. So I'm looking at this bar chart now to see what's happening. Now we can see already the dark areas here are reducing. This dark is gas. So I've said that gas is getting reduced from over time, from 2004 to 2011. Coal remains roughly the same. It does spike in 2008. I mean, you could put that, but we'll have a look how many marks it's worth. Nuclear energy, very much the same across. Oil, again, starts low, it kind of fluctuates. And then renewable energy kind of stays the same. So what have I said? I've said a reduction in grass, and the others remain similar. And I think that is a fair answer for 2 marks there. And then electrical energy. All right, so in 2011, the consumers in Wales used 45,000 gigawatt hours of electricity. Describe the shortfall between supply and demand was met. So what we're looking at now is that in 2011, the total amount of electricity generated in Wales was this. There are no proposals. So it was actually, so what they're saying, this was generated. They're looking to build another power station to generate this amount, but they actually used this. So how was this demand met? So electrical energy, as we know, can be sourced and transferred from other stations in Wales using the national grid, because that's the purpose of the national grid. We're all connected together, okay, for 2 marks. And then it goes on to say, if it had been commissioned, that second one, which is here, okay, oh, sorry, this one by here. If this had been built, then how much surplus, and this word means extra, how much extra electrical energy would have Wales have produced? So I've added the two together, 28 and 23. So 28 from here, 23 from here. That gives me a total of 51,000. But only, let me just change back, 45 was used. So how much extra would we have had? Well, 51 from this minus the 45 from up there gives me 6,000 gigawatt hours would have been extra. Why haven't I answered that question? State the renewable energy source that didn't make the contribution to the electricity generation between 2004 and 2011. So there's 2004, 2011. Which one didn't make it? Ah, right. So we can see already that solar power there is not represented on this graph. Therefore, for 1 mark, this would be solar panels. Okay. That was a pretty easy one. Okay. How many pages I got left? Yeah, I'm going to have to do part 3 of this paper now. Part 3 coming up. Sorry, I just realised that there was one more part to this question. So this is not going to be part 3 yet. For the period considered between 2004 and 2011, total amount of electricity generated in Wales changed considerably. Explain which renewable energy source was mainly responsible for this. So if we look at this graph back up here, I know it's a bit awkward because it's all the way back up here, but you can see wind energy was being used more and more. Okay, so the first part of my answer there was wind shows a significant increase in 2011, whereas other resources remained constant for, between 2004 and 2011. You can use your own graph to look at that, okay? Remained constant. They didn't really move. Since 2011, considerably more Welsh homes had PVC cells. It's not PVC, sorry, just PV cells, which is solar panels installed. Describe and explain how the bar chart could look for 2015. Well, I'll give you the answer first, and then I'll explain my answer. So it says bar chart will be taller as more electricity is generated from these renewable energy sources. Wind may continue to follow the trend, but solar would increase. Now, I'll just go up and have a look, because solar, it's not that graph, it's this one. Solar was only from 2011. So what they're asking you, how would this bar chart look if it continued? So I think wind would continue with this sort of trend of going upwards, and then these bars would get taller because solar is being added to that. So that's what that question means. Okay, I'm going to go to the third part now. Okay then, so this is part 3 of this paper. It's quite a chunky paper because there's a lot of questions on there. We've got a diagram here of the national grid. We've had a similar question before. No, we haven't. So state one environmental advantage of using a nuclear power station compared to gas fire. So gas is going to produce CO2 and SO2 emissions, so sulfur dioxide there. So nuclear is not going to produce any of that. So it's a nice clean energy. Let me just put that a bit straighter there. And then we've got another sort of Sankey diagram coming in here. I got 200 joules going in. I don't know what my kinetic energy, but I do know 150 joules is being lost as heat. So 200 minus 150. So I've got a small arrow there, which is 50. So a nice easy mark there. Percentage, we've looked at this before. Again, you're going to get this from the front of your paper. It's for useful over total. The useful I just calculated to be 50. The total going in was 200 up here, and that's going to give us a 25% efficiency once we times that by 100. Okay, let's go for this. Burning fossil fuels adds to climate change. Yes, it does. Nuclear power stations emit lots of carbon dioxide. That's nonsense. That's not true. This is worth 2 marks, by the way, so I'm looking for 2 correct answers. Tidal barrages damage marine habitats. Yes, that is totally true because they do spoil that area. Waste from gas power stations is radioactive. No, that makes no sense at all. Because gas, why would it be radioactive? Wind power causes acid rain. Again, nonsense. Absolute nonsense. I've underlined this one for a reason, because explain why coal has the greatest effect on global warming. Well, it's got the highest carbon monoxide, okay, well that doesn't, but it's got the highest sulfur dioxide and the highest carbon dioxide there. So these are the 2 we're looking for there. Okay, you can see the others are lower. Oil, nearly there, but okay, this sulfur dioxide is massive. So coal produces most carbon dioxide, which adds to greenhouse gas effect of global warming. I should have said sulfur maybe as well there. But 2 marks, nice easy 2 marks. Then we've got a nice little graph. Oh, this is lovely. Coal and gas. So we got coal. There's the keys. The constant line is coal. The dotted line is gas. I can already see the trend there that coal is going down. It had a little spike between June and January, but otherwise it's going down. And then your gas is kind of climbing there. Okay, it had like few dips in January and maybe between June and January there. But I'm guessing it's going to ask me to describe, use the graph to compare. There we are. So nice comparing. So coal decreased as gas increased from January the 14th. Fluctuated until January the 15th. Coal decreased more as gas increased. So really, just reading the graph, okay, you could, that's the general trend, but you will get marks for pulling figures out, for pulling some dates out and describing the general trend. And then we're on the last 2 pages. So this hopefully is going to be a nice short video. The UK and blah, blah, blah. Let's have a look what the question is. Use the data in the table to compare the percentage of electricity produced by renewable sources. So renewable sources, well, that's renewable. That's non-renewable. In April 2015 and 2016. So April 2015, 2016. So I'm looking at these. Okay, so from April 2015, it was actually higher than April 2016. Oh, decreased slightly. Is your answer what you expected? Not really, because I would have expected us to be between 2015 and 2016, more renewable power stations were built. So I would have expected that to have gone up, the percentage of electricity produced by renewable energy sources. But, bit odd, but we've highlighted for 1 mark, okay, that we are surprised by that. Nice little question to finish with. Give a reason why electricity is important to the UK. There's not enough to meet demand. Okay, so it says there it's imported from France. What time of day is most likely important from France? Well, I've said it spikes there. Look, demand is like 40,000 there, megawatts. So it's more than likely at 6 o'clock when everyone's watching EastEnders. That's when they're getting this electricity from France. Lovely. Okay, hope you enjoyed that, and I hope it's been useful, and hopefully you've got a completed booklet. Bring it in and we'll have a look.